Okay, good morning or afternoon, class. I want to show you how we are going to be using solubility curves in this class. This is, of course, your lesson, which you will then be practicing. You'll notice it's on the back of the assignment you were to have done by now. And this is a version of a solubility curve. Like any good graph, you want to start by reading the axes. So over here we have grams of solute per 100 grams of water. So what that means is all of this information is for these solutes. Here's some potassium iodide, here's some sodium nitrate, so on and so forth. All of these curves were made by dissolving them in 100 grams of water. That does not mean 100 grams is the answer to every question about the solubility curve. I've actually had a student say that. So that's not what that means, but we will come back to how we're going to be using that 100 grams of water later. For right now, you'll notice it is grams of solute, so it's talking about specific grams of each of these dissolved in the water. Then at the bottom, we have the temperature. So this is a grams of solute versus temperature graph. And we have a bunch of curves and non-curved lines. And so this is why we call it a solubility curve. And solubility curves are wonderful tools because they give us a large amount of information for whatever it is we are analyzing in the curve. We're going to start with some generals and then go to some specifics, and I'm going to walk you through all the things that you're expected to be able to determine from a solubility curve. So be sure you're paying attention as you will be doing these sorts of things on your practice. So let's take, for example, potassium nitrate. We see a curve that starts here and goes all the way up there. Okay, so what does this curve mean? This curve was made by determining how many grams of potassium nitrate we could dissolve in 100 grams of water when that water is at this kind of temperature. So you'll notice most solids increase, which is very general to solids. Solids tend to increase their solubility in water when the water is warmer. So we do have a general trend there. I'll point out there is a solid down here that actually decreases in solubility. And that's unusual, but it's not out of the realm of possible. It is okay that that does that. It's just its nature. Get into AP chemistry, we can talk about the enthalpy change associated with that and why it decreases, and that's for next year. All right. Then I also point out we have ammonia right here, which decreases, and ammonia is a gas. So it's not at all surprising that a gas would decrease as temperature goes up. As we determine in lab, you want to cool liquids to help them dissolve gases, not warm them up. Warming them up will allow the gas to escape easier. All right, so this is a solubility curve, and the line tells us how much will dissolve in 100 grams of water at that temperature. So the line tells us that it is saturated. So if I want to know how to make a saturated solution of potassium nitrate, say at 50 degrees, I'm going to follow up the 50-degree mark and see that it takes, over here, it takes 80 grams of potassium nitrate at 50 degrees to make a saturated solution. So I can add potassium nitrate to my 100 grams of water, up to 80 grams of it, and it will dissolve. That will be saturated. If I add any more, 81, 82, 83 grams, that extra will not dissolve. It'll sit there at the bottom of the container, just looking like it's doing nothing. So the line is for saturated. What if I don't have 80 grams even? What if I've only added 60 grams? So at 50 degrees and 60 grams, I'm right here. Now I'm still talking about potassium nitrate. I don't know why that didn't leave a dot. There we go. I'm still talking about potassium nitrate, but I'm right here. at 50 degrees, that is below the line. So below the line is unsaturated. Right. So that is an unsaturated solution because it is below the line and I can still dissolve more. And then what if I, by careful manipulation of temperature and such, what if I were to actually get, say, 110 grams of potassium nitrate to be dissolved at 50 degrees Celsius? Well, now you can see that particular dot of 110 grams and 50 degrees Celsius is above the line at 50 degrees Celsius. Notice how it always comes down to temperature. Above the line at 50 degrees Celsius, that would tell me super saturated. It has extra dissolved in it than should be in there. What should really be in there is about 80. Okay, so those are generals. That's just a general way to read the solubility curve. But it is more powerful than that. We can talk way more about information on this graph than just whether it's saturated, unsaturated, or supersaturated. So let's clear the board. Maybe. Okay, that was supposed to work. Let's clear the board and let's look at some other more specific questions. Again, let's just take this convenient point of potassium nitrate, 80 grams and 50 degrees Celsius. So this is going to kind of be our reference point right there. We're looking for potassium nitrate. The things I'm going to share, of course, would be true for all of them, just in different locations. So I've got right here, knowing that it's saturated at 80 grams in 100 grams of water at 50 degrees Celsius. What if right now I only have 50 grams in there? There we go. So I only have 50 grams in there. Okay, so let's say I only have 50 grams in there. What's that tell me? Well, if I only have 50 grams in there, that tells me I'm unsaturated. But here's the cool part. I can determine how unsaturated it will be. That is, I can determine what's the difference there. I can dissolve 80, but I've only dissolved 50 at 50 degrees Celsius both times. That's a difference. Okay, 80 grams minus 50 grams, if you need to see it. That's the difference of 30 grams, meaning I can still dissolve 30 grams more in that solution of 100 grams of water, and it will all still dissolve. So that's some of the power of a solubility curve. Not just tells us it's unsaturated, but tells us how unsaturated, how much more we can still dissolve in. Also, let's go up with, I do put 110 grams in, but I don't manipulate it. I just dump 110 grams in. Well, if I'm not manipulating it to force it to be supersaturated, it won't. It'll stop at the saturation point. But I've dumped in, just because I felt like it, 110 grams. If I dumped in this is supposed to be 110 grams, and it can only hold at its saturation point 80 grams, but I've dumped in just 110, just a spoonful, then it actually means 30 grams of the solid I dumped in is not going to dissolve. It'll just sit there at the bottom doing nothing. So if I actually wanted to get rid of it, then I could filter it. And the 80 grams that has dissolved would go through the filter, and 30 grams, which has not dissolved and will not dissolve, will be caught in the filter. So it's a way, not only can I determine that it's not going to be supersaturated, I can also determine that it's going to give off 30 grams of solid. I'm going to be able to catch that in a filter. So that is some of the power of a solubility curve. Now let's talk about changes. So let's go to a new slide. Or not. How about we just do it this way then? I wish touch screens liked my fingers better. Okay, so let's go for something different just to have some fun. So let's start here. I have ammonia chloride. It is saturated with 70 grams of of ammonium chloride in 100 grams of water at 90 degrees. Now that's really hot water. So I let it cool, and it cools to room temperature, which on this particular day is 20 degrees. So I'm going from 90 to 20 degrees. Okay, I'm going down that way. And I want to know how much solid will suddenly start forming at the bottom. Well, easy enough to figure out. I used to at 90 be able to dissolve 70 grams. Now here at 20, I can only dissolve, let's say, 35 grams. And I know as you read this graph that it's going to be estimates, so just do your best job of estimating. Okay. And so I can actually do the math now and see, hey, it's going to be giving me 35 grams of solid sitting at the bottom. Or in other words, I could filter out 35 grams of solid after this temperature change occurs. Now the reverse would also be true. If I started with it saturated at 20 degrees and 35 grams, and then I warmed it up to 90, I could see the difference as how much more I can add to get it to, and it would still dissolve. So the beauty of a solubility curve is this ability to predict how the reaction will change and in a numerical sense with the change in temperature. So I could go both directions. I could warm it up, and in most cases that will dissolve more, and I can read from where it started to where it ends and see how much more. Or I can cool it down, and I can read from where it started to where it ends and see how much will precipitate, how much solid will be left in the bottom that I could catch in a filter, something like that. So hopefully you're realizing rather easy ways to read the graph, but this is some powerful stuff for us. So we're able to make some good predictions about the amount of stuff that will dissolve or not dissolve in any of these solutions at 100 grams of water. Now I mentioned earlier this 100 grams of water. Let's talk about that, because there's even more power to a solubility curve. Now this is truly the pinnacle of using a solubility curve. This is some of the best stuff that it can do for us. Let's take something we haven't talked about yet. I don't know. I'm seeing this sodium chloride line that goes right there. Okay, and let's say, wow, I drew my line rather crooked. It looks like at 80 degrees. It looks like at 80 degrees, it will dissolve 40 grams. But here's the thing. I only have 19 grams of sodium chloride. I want to know what's the minimum amount of water I need to dissolve that all away and have none sitting at the bottom and not have to worry about making it super saturated. Well, this is actually an easier question to answer than you think. I'm looking for, if I want to dissolve 19 grams of sodium chloride, and I don't know how much water that's going to take. But I'm at 80 degrees. Okay, I'm at 80 degrees. That's important to know what temperature you're at when you're doing something like this. So at 80 degrees, I can dissolve 40 grams in 100 grams of water, but I'm only having 19 that I want to dissolve. Well, it's just a ratio. If 40 grams of sodium chloride can dissolve in 100 grams of water, see, that's where that grams of water over there on the side is coming in to help us. If I can dissolve 40 grams in 100 grams of water, then how much water will it take to dissolve 19? So it's just a proportion. And I just put X where I wanted it. That is the minimum amount of water to dissolve that. And now I just need to solve for X. So it'll be 1900 divided by, let's see, grams will be left on top. 1900 grams divided by 40. And whatever that's going to be is going to be the minimum amount of water that will dissolve 19 grams of sodium chloride. So that's pretty cool. We can actually predict that. So yeah, I'm going to actually get out my calculator now. And I'm going to take 1900 and I'm going to divide it by 40. And I get 47.5. All it will take is 47.5 grams of water to dissolve only 19 grams of sodium chloride. So notice how very useful that would be. I could use this curve and I could scale it to any amount of water I have. So let's do one of those. And let me switch to a different color. Okay, let's say I have 250 grams of water. Okay. And I want to know how many grams of, we haven't used potassium chloride, or let's use ammonia, let's use a gas. How many grams of this gas at, let's go 70. At 70 degrees, if I have 250 grams of water, how much ammonia, NH3, can I dissolve? Okay, well, let's just ratio it out. Oh, and now it decides to change based on my fingers. Yeah, because that's the way life goes. Okay. I know that 100 grams of water will dissolve at 70 degrees this amount of ammonia. If you will, if you're okay, let's call that 17. And again, I realize you'll be reading from a graph, so it's not going to be exact, and that's understandable. Don't worry, we're going to be able to get exact numbers next lesson. That is going to be coming, but not right now. So, I want to know how many grams of ammonia will dissolve at 70 degrees if I have 250 grams of water, and I know from the curve it's 17 if I have 100. Okay, so we do the math. And it's going to be 250 grams times 17 grams divided by 100 grams. And that's all the math. So I've just broken it down to a nice simple ratio, a proportion. And I'm going to pull out my calculator here and then take my 250 times my 17 divided by my 100. And I see I could dissolve 42.5 grams of ammonia in this case, in 250 grams of water. So it's all proportional. And even everything I said about how much will increase if we warm it up or how much will decrease if we cool it down, even that is proportional to that 100 grams. So anytime you have a question where it's not 100 grams of water, no big deal. Just proportion it out, just make it a ratio of how much the line tells you in 100 grams, and then you can put X where it is needed, whether it's the grams to dissolve or the amount of water. I've done an example of both of those, and then you'll get your answer. So beautiful in that we can get so much predictive information from a solubility curve, and it really works it out to a rather simple mathematics, just nice little ratios. Do your standard crisscross divide sort of proportion work, and you're good to go there. All right, that really, really is all there is to a solubility curve. You just have a bunch of questions to ask about it, doing nothing harder than these little ratios. Some of the questions are meant to make you think, but again, it's nothing mathematically harder than a ratio. Trust me on that. And sometimes, as we saw earlier, it's a matter of simply doing some subtraction to see how much more or how much will precipitate out, that sort of thing. All right, so don't make the math harder than it is, and just spend your time figuring out what the graph is showing you, and you should be okay. Feel free to ask to have this video replayed. I have no problem with it playing over and over again if needed for it to sink in. But again, it's time for you to practice. So be sure you've got the front side filled out. That was your past homework. And now flip to the back where it says solubility curves and answer those questions. Have them ready to trade and grade next time. Good luck.